Hi, hello, and welcome to the Falling Walls Breakthrough Conversations. My name is Naveed. Here with me is Professor Clare Grey. Nice to see you, Clare.
Hi.
Just a brief introduction. Clare is a Royal Society research professor at the University of Cambridge, a world leader in battery materials and nuclear magnetic resonance. She was just recently awarded the Koba Prize. Congratulations. And is the principal investigator of the £12 million Faraday Institution battery degradation project, and is the co-founder and chief scientist of Niablet, a battery fast-charging company founded in 2020. Now, this is not just an opportunity for me to learn more about your research and its implications, but it's also an excellent opportunity for you viewers out there to address your questions and your comments to Clare. So for more technical guidance, should you wish to speak with our guest directly, please use the raise your hand option on Zoom. You will be spotlighted on the screen and unmuted. Hereafter, you may address your question or comment. After you have spoken, we will mute you again. And should you have any technical issue, please address this in the chat, and our technical moderator will assist you. And for everyone to know, the Breakthrough Conversation is being recorded and will be made available in the content library on the Falling Walls website after the Science Summit is over. Dear Clare, so you've spoken earlier today on the stage of the Falling Walls conference. Since we have a fairly interdisciplinary audience here, maybe you could just tell our viewers a little bit about your research.
Well, I spoke this morning on one specific aspect of my research, and that's to design faster charging batteries. And so I tried to explain why that was important and what we'd done as a contribution in that field. But the broader context of my work is in trying to understand how the materials inside a battery work, and specifically developing new metrologies to do that. So to look inside a battery while it's cycling, so operando, without having to tear the batteries apart. And so you might want to do that because it's a very efficient way of following what's going on, but you also might want to do it because you can pick up things that you wouldn't see if you pulled the whole batteries apart. And so my research spans very much the materials to the fundamental understanding, developing of the metrology to do that, now all the way through to a startup company for fast charging.
And how do you, because you just said you can basically see into the battery, how do you do that?
Well, we use a variety of different techniques, but the technique that my lab has helped to pioneer is to use an NMR spectroscopy. And so this is a technique like MRI, which you might be familiar with in a hospital, where you sit inside a magnet and you look at the water in your body and you image your joint or your particular part of the anatomy. What we do is we use the lithiums. They also give a signature, and we can map the lithiums out inside a battery, or we can do spectroscopy. So in hospitals, that would be via functional MRI, where you look at a specific environment around the protons or the phosphorus in your brain. In a battery, it would be looking at the lithiums and the local environments around that. And that allows us to look at, for example, lithium dendrites that form, safety issues, to look at ion transport, to look at how materials evolve.
Interesting. So I'm not a chemist, of course, so you're the expert. Maybe just a very, let's say, simple question, perhaps, but is it possible to apply this this way of looking at batteries with all batteries? Are they all somewhat the same, or?
Well, I think you've asked two different questions. So first of all, the easier one, no, not all batteries are the same, but our particular technique is better suited for batteries that we design in the lab. And that's partly because we can't get the radio frequency fields through metal cans in a battery. And so what we try and do is design batteries that are as close as possible to real batteries in the field so that we can still look at them under realistic conditions. But we don't just do NMR spectroscopy. We're also interested in other diagnostic techniques. So I work with colleagues to, for example, put Raman, other spectroscopic probes into batteries to shine X-rays through them so X-rays can penetrate through a can, and there we can actually look at real inverted comma batteries. So we do both. I mean, I think it is important to both look at these, what I would call a bespoke battery, one where we've designed it expressly for our technique, but also to develop methods where we can look at real batteries, so that you can imagine a world where you're driving along and maybe you've applied your brake too strongly, so you've charged your battery too quickly, it's heating up, and you get a signature saying, look, if you carry on driving like that, your battery will fail faster, or slow down, mate, otherwise you're going to get degradation. So it's that sort of ability to in real time track degradation is what I'm also interested in.
Mm-hmm. Now, you're doing fundamentals research. You've co-founded Niablet. Could you tell me a little bit about how this translated into something that is, very much dealing with applicability as well?
Yeah, so we, in my lab, a former student of mine, Kent Griffiths, and I came across a particular anode material that enables the lithium ions to move out very rapidly. So we put it together with a cathode material to make our fast-charging Niablet. And now we're spinning this out, but what we're trying to do is to think about applications where fast charging is really important. And the obvious ones, you start off in a small company in particular, you start off with power tools, robots. We would like to come up with the battery that when you run out of the new petrol, so when you run out of electricity on the side of the interstate or the motorway or the autobahn, we will be there with the battery pack that will charge you and get you going to the next power station. So that's what we're trying to do, but of course you've got to go from the lab to then developing and manufacturing the cells. You put a battery, and every battery has a different characteristic of current and voltage. So you've got to build the whole engineering around it. So with each battery is a little chip with a battery management system, and so we've assembled the team to do that as well. So it's just all the way from the chemistry to the whole engineering part. Mm-hmm. So it's exciting.
Has that somehow changed your perspective for fundamental research? Because now you've you're in a new kind of realm. Does that somehow influence?
It's a question, often I get asked, but I've always been of the sort of person who has been motivated by the application. So I started off as a scientist. I spent 2 years at DuPont Central Research, and I was interested at that time on phasing out chlorofluorocarbons, and we were interested in new molecules to do that. So I had always... My work had been very inspired from the environmental or the technological perspective, because it sort of gives you a new insight into what needs to be solved. So more recently in the battery space, being in the company space makes you want to worry about not just one component, the whole system together, because it's very simply in a battery you've got an anode and a cathode, and our discovery was on the anode, but to get it to work you have to also get the cathode right. And these two, they operate together, and there are synergistic mechanisms where one affects the other. And so the other thing I do is I lead the UK's activity on battery degradation. And so there we've had to understand all components of the cell in batteries that go into electric vehicles. So yeah, I think it does change the way I think, but I also am at heart of a fundamental scientist, and I think that's very critical, that to solve some of these battery issues, you've got to get down to the atoms level and understand what those molecules are up to, because those molecules have got to be doing their things for many, many years if you want your battery to work for that long.
And could one say that, of course, fundamental research is curiosity-driven. It's a different type of pressure as well, perhaps, and that's important in order to...
Yeah, but I think people always say this curiosity-driven, and it sort of gives the impression that we're all dilettantes, and just. But I mean, we're more than that. I mean, it's not. It's you're asking fundamental questions, and even if it's not directly applied to something specific, you're always trying to pull out lessons from something, and trying to see how what you've learned about a specific system translates to a bigger system. And so I think you can afford, there's this debate that goes on about blue sky science versus applied scientists, but even if you're doing blue sky science, you should still look at what you've done and try and work out how that has relevance beyond the specific system that you're looking at. So I always try to do more than curiosity science. I think it is literally trying to think about the bigger picture at the same time as doing the small stuff, because you have to do both. You can't deny the fact you need to work out what's going on at the levels of atoms.
Right. And speaking of the bigger picture, now we have a fairly diverse group of participants at Falling Walls, not just physically, but also digitally, representing not just academia, but also policymaking, the industry, and also the general public. What kind of impact will your research have on society? What implications will it have? Is there, maybe even an industry specifically that is impacted by it more?
Well, I think that's almost an impossible question to ask, because you're asking me what are the impacts of batteries? And again, as I try to articulate in my talk, they go from the small level to all the way through to big batteries on the grid. But thinking even at the small level, the Internet of Things is going to have trillions of sensors, and those sensors will be powered by batteries. And so you will have them, they will be omnipresent. And so we need to think about batteries that could last longer. Otherwise, people will be spending hours and days of their lives changing all of these batteries. But so I can't even answer your question, because the role of batteries in our modern life is so pivotal.
Right. But would you say, for example, if we're looking at this from a climate action perspective, is there an industry that could be a vehicle to drive this more, that is based on?
Yeah, well, maybe I'm not getting my message across very clearly. From a climate action point, it's electric vehicles, electrification, and storage on the grid. So if you want to enable renewables, and you need to deal with intermittency. And so the battery plays a role in short-term regulation, so balancing supply with demand. And in the next generation of batteries, and this is what I'm also trying to work on, is trying to design more sustainable batteries that are cheaper, so that you can make bigger ones without having too many resource implications. And then we can start to push further into longer term storage, not at a level that competes with hydro, but if you think about then small microgrids in smaller communities, you can imagine battery storage. So yeah, the battery has, it is very much part of the climate solutions. And the debate at the moment is, where batteries, where hydrogen, and that's a whole conversation we could have. But I think the battery is fit for purpose in many applications now, and the challenge then is to move into a bigger space and make an impact, because it's one of the biggest challenges at the moment. And today is Science Day in COP26, and so it's exactly these types of developments that are needed to move the world away from coal. And if we're going to do this globally, it has to come via cheap solutions to technology. And batteries will make impacts in some markets, not in all markets, but definitely in a lot of them, and a lot that will make impact. Right.
So you're working on fast charging, you're working on the longevity of batteries. What about the recycled usage of batteries? Is that somehow an element or a part of your research as well?
Yeah, I think the battery recycling should be a part of my work. At the moment, our focus, because we're doing the fast charging, is thinking about batteries. Because you can cycle them faster, you won't have to have such a big battery. If you look at many of the car companies at the moment, their strategy to fast charging is just to be big. You have a big battery that buffers the fast charge, and that has tremendous materials resources implications. And so if you can start to rethink that with fast charging, I mean, there are challenges. Intrinsically, our battery may not have the same high energy density. It's good, but it's not the best in class. But I think as we move forward as a society and we think about how we're going to electrify everybody, there will be compromises. I don't think we can all have the equivalent of the Mercedes, the Teslas, the Porsches, and whatever. That society is not going to be able to tolerate that. And so how do we do this in a just way? So going back to recycling, it's an area that I think is intrinsically very important. We need to think about how we build these batteries from scratch so they can be recycled in a safe way. And you've got components in those batteries that are not inherently safe when they're pulled apart. And yet we've got to fix that problem. And then we've also got to fix the problem of the second life. And how you place a value on that battery. And placing a value requires that you understand how it's going to degrade. And there are modes of degradation where batteries gradually fail, and there are other ones that go off a cliff. And if I'm going to sell you my battery, you'd like to know that it's going to go the way you predict. It's not going to be the one that completely tanks. And so this goes back to my research that I was talking about earlier in terms of measuring, trying to track the degradation mechanisms on the intact battery before they fail, but also before a safety incident occurs. So that's very important. So I think recycling and longevity and second life are all part of the story.
Great. Thank you, Claire. We've got a question from the audience. So please go ahead.
Thank you so much. Hi. First of all, congratulations on your recent prize. I think this is a very big achievement.
Thank you.
Second of all, my question would be, so we talked a lot about fast charging batteries, and then I thought that obviously you say yourself that the most interested parties are not only people, but also businesses. They're interested in the technology. And I was wondering, how do they support your initiatives and your research, and if they're included anyhow, or you're reaching out to them and ask for any help, like funding or stuff like that. So we'll be really interested to know that.
Well, I've been very lucky to have industry support in different ways. Within my own fundamental research, we have some industrial contracts with industries, and that's about as much them helping me, but also me helping them in terms of understanding how various materials function. But in terms of the startup, then we're working our way through as a traditional startup role. We're about to start Series B fundraising. And so that will directly ask for people to invest. And, the battery field is very tough because we have to now start to manufacture. And you've probably heard about the landscape of the gigafactories. Those are multi-million projects, and that's very difficult for a small startup to do that. So you have to sort of gradually build up. And so right now we're into our next round of fundraising to do into the second round of fundraising to actually now build and manufacture, to demonstrate, to put our batteries into lots of different applications. So yeah, we definitely have to rely on both industry funding or to help motivate the more research-based activities, and then now a combination of venture capital and some industry for the next stage. Thank you.
Thank you. Maybe one final question before we conclude this interview, and maybe a slightly personal question, Claire. So how did you get into this field? What sparked your interest?
Well, it's a funny story, actually. I've always been interested in environmental questions and trying to connect my very fundamental science through to applications. But I gave a talk in a conference, and I was actually talking about fluorine. And a dear friend who sadly died came up to me and said, "Claire, I loved your talk on lithium." And I didn't want to say to him, "Look, I wasn't talking about lithium, I was talking about fluorine." But he said, "No, come, why don't you look at my batteries?" He was from Duracell, and so he gave me his batteries, and he asked me to apply my technique, NMR spectroscopy, to them. And there's something quite difficult about this particular method as applied to them. And so I went back into my lab and started to look at them, and I realized I couldn't understand how to interpret the data. And it took me 2 years to figure out how to do it. So I went back to him and said, "Bill, I know how to do it." And he said, "Tough, we've canceled the program, but we'll fund you to do something else instead." So that was, and at the same time, I was playing squash with friends of mine from Brookhaven Lab. This is in the US, and they were also electrochemists. So based on the squash games and our interactions, I managed to get my way into that lab and use their pieces of equipment and send my students. So serendipity, but also, again, this idea of trying to think about ways of using my methods to do things. So like many stories, there's a lot of luck in it.
I guess that's just life.
Exactly. But it's sort of seeing the luck and then making...
Yeah.
Taking the advantages of the luck that you get and doing something with it. So,
absolutely. Nice words to end on. Thank you very much, Claire. Thank you, everyone, for joining us for this interview. We will be back in a few minutes with another interview with Eric Backers and Elham Fadali, who also spoke at the Falling Walls conference. See you soon.
Thank you. Thank you.